Our discussion continues with Scott Wharton, CEO of Tandem PV. I'm Reimagine, and this is The Tech Between Us, and we're exploring the new material innovations in solar capture. Now let's jump back into the conversation. Let's talk about the differences between the Tandem PV solar panels, the perovskite-based panels, and just traditional silicon panels. I know with silicon, there is actually a theoretical limit on how efficient these things can be. Is perovskite more or less than silicon?
We've come a long way with silicon, both in terms of cost reduction and also making it better. So today, the average silicon panel in the U.S. is about 21% efficiency. So basically, 100 beams of light hit it, you can convert 21 into power. So the way we're doing it is we're stacking up the perovskite panel on top, mechanically, on top of silicon cells. And we are currently at 28%. So about 30% better. Our expectation is that we will exceed 30% this year. We've been adding about 1% improvement a quarter, which is fast. Given the historical changes.
Right.
And the theoretical limit for silicon is probably about 26%, where they just run into some constraints based on the laws of physics.
So silicon's actually getting close to that theoretical limit now.
They're getting pretty close to that and hitting diminishing returns, whereas perovskites, the theoretical limit's in the mid-40s, maybe even up to 50% if you stack three things. So we've got a lot of runway to go to improve.
And now, through your R&D processes, through prototyping and whatnot, you said you're getting 1%. Once again, is that something that's going to continue to improve throughout development? Or do you think you'll hit a point where it's like, okay, these are good enough? You can kind of get that cost versus performance ratio and really hit that market hockey stick.
Well, look, if we're at 28% and the theoretical limit's in the mid-40s, we've got plenty of room to continue to improving. So my expectation is that can we continue to improve at 1% a quarter? At some point, probably not. That's really amazing progress. But our plan is that in the medium term, we think we can get into the mid-30s without any material scientific breakthrough, just incremental improvements. On both the silicon will keep getting better, our stuff keeps getting better, and then there's the way we integrate them. So those are three areas to continue to improve. And we also expect that we'll be able to continue to drive the costs down through process improvements of things that we'll learn by moving from small manufacturing scale to larger scale. So I expect that we'll continue to get both better and cheaper over the coming years. And why is that important? Because I think the listeners know that there's going to be insatiable energy demands.
Right.
That we're not in this world anymore where we were kind of flat for a long time. I think there was this view that, we'll be flat and we won't need any more energy and we'll just become more efficient. The reality is there's AI, there are electric cars. Everything that we use in modern life is becoming electrified.
Right.
And of course, we're talking about just people who live in the Western countries, but people who live in the developing countries, they want what we have too. So there will be insatiable demand for electricity, I think, for the foreseeable future, for the rest of our lifetimes. And I think part of what we need to do is both provide that, but you already heard that there's kind of no constraint or demand, unlike oil or other things. So I think this could go really, really large, where there's no limit to how much electricity we can have. And the constraint on human culture and human economic productivity has always been tied to electricity and power.
Absolutely. All the major industrial revolutions, have that component to it.
So if we want to be able to achieve that in AI and other areas, we need this technology to be able to go to the next level. And if we want it to be equitable too. So it's one thing to have people in the U.S. to say, okay, we've got a lot of power and we're just going to transition it from oil to renewable stuff. But you can't really tell people in Africa and Latin America, hey, that one light bulb you have? Oh, now it's going to be green, but you got your one light bulb. They're going to be like, to hell with you guys. We want to live the way you do.
Exactly. Simply by transitioning from silicon panels to perovskite panels, getting that 30%, which is current, and it sounds like that's going to be just ever increasing as well. That could mean, terawatts of power, of additional power, simply by this material change from silicon to perovskite on a global basis.
I think so. Just to put that in context too. So last year in 2024, the world deployed 600 gigawatts of solar power.
Okay.
Now, to put that in perspective, that's in 1 year. Usually a nuclear power plant's about 1 gigawatt. So it's 600 nuclear power plants in 1 year.
Wow.
Now, half of that was in China. And China deployed 300 gigawatts. So China deployed more solar power last year than the United States has done in the last 68 years. China today does about a third of all emissions. So when you talk about global warming, it's not really a global problem. It's a China problem. Because the U.S. and Europe are roughly flat.
Right.
The developing countries in Africa and other places, they're still relatively small in terms of their emissions. So it's a China problem.
Okay.
China only recently committed to kind of capping their emissions, and they said they would do it in 2030. But the good news is actually they've kind of peaked in 2024 already.
Okay.
And a lot of that is because of their solar deployments, and that's only picking up. So, I mean, there's some good news for people listening that while there are terrible things happening around climate change, I think we're in the process of doing the things that we need to do to solve it in the medium term. Now, I think
Right.
doing it in 20, 30 years, it's not fast enough. So part of my personal motivation for diving into this is, look, it's got to be faster. And I don't think
Right.
you get it through yelling at people or, even in governments. Governments go up and down and they change their policies. You can only
Right.
really do it by having people do it because they're greedy and it's better for them economically, I think.
So you do have an optimistic outlook for climate change.
I do in the medium to long term. I
Got
would
it.
say in the short term, I don't feel complacent about it.
Right. Yeah, complacency is definitely not a good thing. So when you're talking these gigantic installations, not a day goes by without me seeing somebody on TV or getting a pop-up ad somewhere telling me to put solar panels on my house. How much of the overall landscape is that going to be? In other words, if every man, woman, and child on the planet puts a solar panel on their house, is that going to move the needle at all?
It will, but one of the things I would say is I think we think of solar as only being on someone's roof, but in the U.S., I think less than about 10% of the solar deployed is residential. More than 80% of it is actually these solar farms that you see when you're driving along the highway,
Okay.
and then specifically in places like Phoenix, but all
Right.
around the country. So our focus is on solar farms because I think it moves the needle more. It also has the benefit of you get economies of scale
Okay.
when you put it into these solar farms. And it actually doesn't require that much land. I
Really?
read an article and I posted on LinkedIn the other day that there are 10 countries in the world that have more space for golf courses than solar and wind combined. The U.S. is one of them. I don't think we go, maybe some people do, oh my God, the world is falling apart because we have so many golf courses. No, I mean,
So putting solar panels on golf courses, that could be a thing.
it could be a thing.
There you go. No, so looking at it from an engineering standpoint, once again, our core audience are design engineers. How difficult is that transition going from traditional silicon panels to the new tandem panels? Is it going to be a massive change of infrastructure? And how do you see that playing out?
Well, it shouldn't be. I mean, one of our approaches is to try to match it as closely as possible to the current infrastructure and balance of systems so that we're not creating a big change. So, for example,
Okay.
we're creating a solar panel. The current standard today is about 1.2 to 2.3 meters,
Okay.
about 2.8 square meters for utility scale panels, a little smaller for residential.
Okay.
We're going to build the same size, and it's going to be roughly about the same weight. And we even have the two terminals coming off of our solar panel. So it's going to look, from an electric point of view,
Uh-huh.
kind of the same.
Oh,
Same
okay.
balance of systems and everything. No, it should be, probably little tweaks and stuff, but almost the same. So
Sure.
our strategy is really to make it as the least disruption as possible. Kind of, we call it as drop-in technology.
Okay, got it. Yeah, because I know a lot of times, moving from one material to another, you get these wild swings in voltages and wild swings in drive current or whatever. But for these new panels, it really, like you said, I mean, they are you unplug one, you plug in the other one, and you get 30% more energy coming out of it.
Well, it's interesting that they do have very different, perovskites and silicon have very different electrical properties. But what we do is we do a voltage matching
Okay.
between the panel itself. So when we hand it off to the utility grid infrastructure, it looks the same. You wouldn't know the difference except that a lot more power is coming off the panel.
So you guys have done the hard work of getting the voltages down to where they currently are and matching, this, that, and the other. And so, yeah, to the installer, they just, like you said, unplug one, plug in the other, 30% more.
Yeah.
You've talked a lot about how much more efficient these perovskite, the tandem panels are. What other advantages do perovskite give?
Well, one other advantage is it's much better for the environment. It only uses about
Okay.
10% of the energy to make a perovskite watt equivalent than it does for silicon. So from a scope 3 emissions, just the amount of energy putting into it. When you're creating a silicon panel, it's a semiconductor, so you have to heat it up to thousands of degrees Celsius. Ours is much lower temperatures, so it just uses a fraction of the power. That partly speaks to the lower cost. That's one advantage. The other advantage is that perovskites are pretty good in terms of having power late in the morning and late in the evening. So kind of, I call it shoulder times, because as probably many of the listeners know, we get a lot of power peaks during the day. So to some extent, in the middle of the day now, from the utility point of view, the power is cheap. It's abundant. They have a lot of solar. Now, you can capture a lot of that with batteries. But one of the things we do is provide more power on the shoulder sides because perovskites kind of, I would say, wake up faster to the sun than silicon does. Now, even though we can probably provide about 1 or 2% more absolute power, it may be worth 10 or 20x because the power is actually worth more at that time from a capacity point of view. And then there are some other really interesting applications because our stuff has an ink and it's so thin. Right now, we're putting it on traditional solar panel glass, but has the ability to put it on plastics and flexible substrates. And, there are some, I'll give you a couple of examples that are kind of exciting. So at CES this year, Mercedes had something they announced where they put paint on a car. Now, they didn't say what it was, but it was perovskites. And so you put this paint on the car, you get about actually 20 miles per gallon through a paint. I think that's pretty cool. Anker, the company that I think many of us know for having backup batteries, they had a perovskite-based umbrella at the beach. Now, first of all, maybe you shouldn't have your electronics at the beach, powering your music player or whatever, but these are like cool applications. But you could think about windows or maybe even your clothing. You got a perovskite-based jacket when you're hiking. I mean, you could kind of basically put power into anything.
Just once again, just because of the properties of perovskite, it's an ink, not a rigid, just like a silk screening on a T-shirt. Instead of putting, a design on a T-shirt, you actually put a layer of perovskite and you're generating energy.
Yeah, in a way, yes. Another application is that perovskites are actually really good at capturing indoor light. Silicon panels are not. They're only really good for outdoor light.
Right.
So in theory, you could have a much better capturing of stuff indoors and in offices. So think about all consumer electronics that we use. Some of them are solar, but they're not that efficient. You can get way more efficient and more power for a lower price by using perovskites in an office.
And I know, one of the huge issues right now is just, everybody leaves their chargers plugged in because they want, they need, power, whenever. And just the leakage current from those chargers are consuming a huge amount of energy. And so with indoor perovskite power source, that mitigates all that.
Well, I think what the listeners know is that anything that we have that's more abundant, we're just going to use it more.
Right.
I don't necessarily think that's a problem if it's clean. And low cost. So, for example, most of the people sitting here either have a phone, hopefully in their pocket, not in their hand right now because they'd be listening to us. And 99% of the time, the processor is not being used. We don't go, oh my God, the processor is not being used. We're wasting it because we have a lot of processing power.
Right.
With energy, we're not quite there yet. But as the energy gets cheaper and cheaper with these kind of applications, I expect that people will find a lot more ways to use it, maybe waste it, but... So what?
Right. It's free.
It's free or near free, marginal costs of very low.
Right, exactly. You've probably seen a lot of these outlier type of applications. Well, how do you feel about those? Is it going to drive the technology in the industry forward, or is it just somebody's just having fun with that?
Oh, I think there'll be a whole bunch of new applications that weren't presently possible or economical that you'll see. It's kind of like any industry where you look at AI and people go, oh, I can apply it here, I can apply it there, or the way people use their mobile phones. So I think energy is a platform, right? So the more we have it, the more uses we're going to find it for other things. We'll do more things. If you think about a world where energy goes from being scarce and expensive to close to free, I think we'll find new applications, maybe even new industries.
Right.
That will pop up based on the idea that energy is near free. So I think right now we're focused on the largest deployment, which is utility scale. But I'm excited for the future about taking this application, whether it's us or other players, and using it to all these different ways of using power to create things.
Okay. Yeah. Stay tuned on that one. Excited to see what pops up at CES next year.
That's right.
Scott, I'm going to ask you now to get out your crystal ball. Where do you see solar technology, specifically here, the perovskite technology, say in 20 years? As you were mentioned before, perovskites themselves are fairly new. Where do you see this in, 20, 30 years from now?
So there's one of the leading market research firms in this space called Rethink Energy, and they did a forecast on perovskites, and they said by 2040, 15 years, not 20, they said that more than 90% of all solar panels in the world will be based on perovskites. for all the
Okay.
reasons I just said. So
Right.
I think they almost, they felt like they couldn't say 100%, but, essentially almost 100%. So I think the market will convert to perovskites. It's just a matter of who does it. Is it us or
Right.
someone else? I think that's going to be part of the fun of capitalism and how these things go.
Right.
So that's number one. I think number two, I've already told you that we're at 90% of new energy being solar, batteries, and wind.
Right.
I think we will get very close to 100. In 20 years, it'll be 100%. There will be no fossil fuels. Maybe there'll be fusion by then, but I think all the others like fission and other technologies probably will not be deployed. And the reason is not because of environmental reasons. They're just cost.
Right.
People
Cost
will
and-
deploy the cheapest thing.
Right.
I would say the other thing that I think people don't realize is that the parallel path between solar and batteries is really going to get rid of this idea that renewables are intermittent power sources. And I've been talking to a bunch of people in the battery industry. So where we've gone, like I said, batteries are 70% cheaper, but they're getting cheaper all the time.
Right.
And there are new kinds of batteries that go longer duration, different applications. So what's happening is batteries 3-4 years ago, there were no batteries in our power grid. Now, there are tons of batteries in the power grid. California is doubling every year, as an example.
Right.
And they went from 2 years to 2 hours to 4 hours to 6 hours to 8 hours. Pretty soon, you'll have, if you have solar and you over engineer it because it's cheap,
Right.
and then you capture it in batteries, you'll take care of this base load problem. You won't need any more. Now, if you're in most of the middle of the world, along the equator, you don't need a winter or summer power because it's like 12 hours a day.
Right.
But there are a bunch of new power technologies or battery technologies that will store longer durations. Instead of hours, they'll go weeks or months or years. I think what you're going to see in 20 years, it'll pretty much be solar and wind and batteries, and that's it. The majority of our power, and we'll shut down all the coal plants by then. Maybe there'll be a little bit of natural gas in there for peakers, but those are already going away. And part of the reason why they're going away is these batteries get more powerful. You actually can't even finance a fossil fuel plant because if they're only running a few hours a day, they're not economical.
Right. Yeah, and back to your point on nuclear, I know, for example, I know Japan's getting out of nuclear, Germany's getting out of nuclear, so it really isn't even a consideration anymore in a lot of places in the world.
Well, I would say, even if you're not doing it for political reasons or environmental reasons. So, for example, I gave the example of China. I think we all probably would agree that China is less concerned about their people's view on environmental challenges like nuclear. China last year deployed over 90% of their power from solar, wind, and batteries.
Right.
Same as the United States. So they are deploying a little bit of nuclear and coal and other things, but it's tiny.
Right.
And it will probably go away. Not because they're being environmentally friendly, it's because they have the cheapest source already that they control. Why would they put in nuclear that would be deployed in 3, 5, 10 years when they can deploy solar tomorrow?
Right, exactly. Yeah, that's another thing. Yeah, nuclear takes long, but even coal plants take years to install and get up and running, and before you even see a single watt of power coming out of it.
Yeah, even natural gas plants. GE, who's one of the leaders in natural gas, they've got a 2-year backlog. So you can't just snap your fingers and deploy a gas plant.
Right.
First, you got to order it, and there's a backlog, and it takes time to install these things. Anybody who's seen a gas plant knows it's not like installing a new door.
I bet not. So, Scott, perovskites are relatively new. Are you guys looking at anything newer, a material even beyond perovskites currently?
No, I think perovskites will be the winner for the foreseeable future, but there are a bunch of ways to improve it. So what we talked about, we're continuously figuring out ways to have the efficiency go up. We're continuing to figure out ways to make it more durable over time.
Okay.
There's still a lot of runway to improve that. We're continuing to figure out a way to make them cheaper. Probably a couple of the vectors that we would work on is right now, I think I said, we have perovskites and silicon. And the reason why we do that is silicon is just very well understood.
Right.
It captures a different part of the light spectrum. So we basically have perovskites are so thin, so we let about 40% of the light through.
Okay.
That's how we get this tandem effect. Sometime in the future, we'll get rid of the silicon because if you can do something at 100 nanometer scale, you can get rid of the silicon. You'll do a perovskite on perovskite layer. You might even do like a triple tandem with 3 layers. So there's a whole bunch of ways to continue to improve there. And we talked about all the new applications, which I think there'll be no limit to the ingenuity of people applying this in different ways. So I think most people agree that there's really nothing out there that is more exciting than perovskites. But we're still in the early days, and it will take time, and we have to do all these things. It's a small amount of engineering work.
Interested in more of our conversation with Scott Wharton? Subscribe to Mouser's Empowering Innovation Together technology series. You'll unlock the concluding discussion and exclusive access to technical articles, videos, and more. Sign up today at mouser.com/empowering-innovation.